Okay, so here we are back at talking about Unit 4 here in AP Physics C, which is linear momentum. Officially, it's called System of Particles and Linear Momentum. So let's talk about impulse now. So in the last video, we talked about change momentum. So let's talk about this impulse. So what happens when objects collide, both objects are going to be deformed because of the large forces that are involved. So here's our tennis ball scenario. So we are in our last example problem, right? We gave the tennis ball 825 Newton worth of force, but guess what? Remember, then means the tennis ball is going to push back on the tennis racket at 825 Newton. So it'll deform. So you can see the ball is squished. The racket strings are kind of like bowing there. So the forces are large because the time interval for most collisions are in the milliseconds range, right? In the example problem, it was 4 milliseconds. Sometimes it's a shorter time. Sometimes it's just a little bit longer time. Now, what we can do is in the last video, we rewrote Newton's second law as delta P over delta T, or M delta V over delta T. But remember, delta V over delta T is acceleration, which there's our Newton's second law. But we also talked about in terms of this was average, and we talk about in terms of instantaneous, we would do dp dt. Okay. Now, if we do some algebra and calculus with that last one, we're going to end up with this concept that dp equals the integral of f dt. We're going to leave it written as dp, but we can replace the d with our delta symbol. And so it's going to tell me that delta p is equal to this f delta, the integral of f delta t. Now, when you see integral, right, you think area under the curve. And on a force versus time graph, which you see here, the area under the curve is something called impulse. So J is equal f delta t. Now, your limits of integration would be from initial time to final time. So impulse is the exertion of a force over a period of time. Now, when we write it in this regard, and I'll just throw an equal sign here, that tells us that this is known as the impulse momentum theorem. Last year, or in an algebra-based course, impulse momentum theorem is just simply m delta v equals f delta t. It's just a reworking of this equation, this m delta v over delta t equation. Okay. Now, if we know the impulse and the time interval, we can figure out what was the average force. So these two shaded areas are equal. One is telling me like the impulse, the other is telling me how to find the average force. And sometimes you actually see on these graphs, they show them as an overlap, right? They're just saying that those two are the same. If you go to NHTSA, the National Highway Traffic Safety Authority, they have crash test data there in which they show these graphs, or they show that graph, and which will allow them to find that graph to tell you which one is the safest car. Also, helmet technology in sports and bike riding and skateboarding and all that is a direct application of these impulse momentum theorem or impulse force time graph equations or force time graph scenarios. Okay, so let's look at an example using calculus. So force exerted by a bat on a baseball is given by the expression F equals 2 kT. So again, even though I'm telling you that this is a calculus question, notice that the force is given with respect to time, which is telling you that you got to use calculus. Okay, this is not simply just a force as a number, but it's giving you that force varies with respect to time. Okay. Now it's telling us that the bat was in contact with the ball for 0.145 seconds. What impulse did we give the ball, and what was the average force exerted over this time period? And so these are going to be expressions because we don't know what K is, right? So we're going to find impulse in terms of K, and we're going to find average force in terms of K. So I'm going to start with my impulse equation. So J is equal to the integral of from 0 to 0.145, my time period, of f dt, but f is going to be that 2k t. And I'm going to do this calculus slow by factoring out a 2k, or not factoring, but because 2 and k are constants, I'm going to pull that out. So it's just simply the integral of t dt, which then tells me I have 2k. The integral of t is t squared over 2. And we're going to evaluate that from 0 to 0.145. That 2 cancels that 2. So it's like kt squared evaluated from 0 to 0.145. And so now I just plug in my 0.145 into t. I square it, and I end up with 0.0210 k. So that is J in terms of whatever this K value is, right? Sometimes there are these coefficients associated with baseball bats. It's a big safety thing. Now, if I want to find the average force, right, I'm going to take, remember, J is equal to delta P. And so that's telling me that I'm going to do this expression, 0.0210 K, in my time interval. Okay, and then I find that my average force is 0.145 K. Again, if I give you what K is, you can figure out the actual force. If I give you what K is, you can figure out the actual impulse. But these are expression type questions just to give you a feel of how calculus is used here. If I was looking at a force versus time graph, it would look something like this. This area would be 0.0210 K. Okay, and then if I take it, and there's my average force, I'm saying from this period, so this blue rectangle would be 0.145 K. Okay. All right, so now from here on out, we're going to look more deep into conservation momentum with collisions and explosions and so forth.